So a common idea that we have when we're doing big O analysis of a function is that only the leading term matters. Only the leading term matters. And this relates to what happens when I add two functions together. So for example, let's just go right into some examples before we state the theorem. So here's my examples. And so sometimes we might have seen, and maybe you've even seen examples like this before, n squared plus 2n plus 1, and then we say, oh, the leading term is n squared, and what that means depends on context, but here it matters that it's the highest exponent, it's the leading term in the polynomial. The leading term is n squared, and so this polynomial is big O of n squared. Or here's another one, n times log n plus log n. Well, there the leading term is n times log n, and so this is big O of n log n. The plus log n doesn't matter, that's smaller. Or 2 raised to the power n plus n raised to the power 100. We haven't learned this yet, but it's the case that exponentials, things where n appears in the exponent of a number, grow faster than polynomials, things where n is something being exponentiated. And so here too as well, the 2 to the n is the dominating term, and so this is big O of 2 to the power n. Okay, so what's really the theorem that justifies this? Here it is. So the theorem is that if I have two functions that I'll call f1 and f2, and f1 is big O of g1, and f2 is big O of g2, then the sum f1 plus f2, so this is what goes on when we add two functions together here. What happens when we add two functions together is that they are big O of g of n, where g of n is a new function. And what that function does, it just takes the maximum of g1 and g2. So whichever of these g1 or g2, whichever of those are larger, that's going to be my big O bound. And so here we can see this in action. So 2n is big O of n squared is big O of n squared, and so when we add them together, the larger one wins out, and so we get big O of n squared. So this theorem justifies the idea that only the leading term matters if we're able to identify what the leading term is, and there's rules for identifying the leading term that you'll find in your reading. If we can identify what the leading term is, then whatever of the g's we can pick, whichever one is larger, that's going to give us a big O bound. So let's go ahead and actually prove this theorem. And we're going to prove this theorem using the definition of big O notation. So here we are. So what we need to do is we need to first, this is a direct proof, so what we first need to do is state what we are assuming and then cache out the definitions. So let f1 of n be big O of g1 of n, and let f2 of n be big O of g2 of n. So I'm just stating my hypotheses. Then there must be witnesses to both of these big O relationships. So there's actually going to be a total of 4 numbers now. I'm going to say C1 and N1, and C2 and N2. So these are our witnesses for these two relationships, and by definition that means that there are two inequalities which hold. So the first inequality is f1 of n in absolute value is less than or equal to c1 times g1 of n for all n greater than n1. And second one, f2 of n in absolute value is less than or equal to c2 times g2 of n for all n greater than n2. So this is just me cashing out the definition of big O notation. It's what I'm assuming in my hypotheses. So now what I need to show is that the sum is big O of g of n, where g of n is what I chose here. And in order to do that, I have a little bit of setup to do. So I'm going to call it n star be just whichever of n1 and n2 is bigger. Whichever one's bigger, I'll just pick that. And I'm also going to let, similarly, C star is going to be whichever of C1 and C2 is bigger. So now I've set up N star and C star. I'm going to also finally assume that I'm going to look at an N and I'm going to assume that N is greater than or equal to N star. And I'm going to show that an inequality holds. So here we go. What am I going to do? I am going to consider the absolute value of f1 of n plus f2 of n. And what I need to show is that that is less than or equal to a constant times g of n, where g of n is this maximum function here. Okay, I'm going to get started. How do I do it? The first thing I'm going to do is I'm going to break up this sum into smaller pieces. The absolute value of f1 plus f2 is no larger than the sum of the absolute values f1 of n plus f2 of n. This is a property of the absolute value that is often called the triangle inequality. Triangle inequality of the absolute value. Okay, but now I know something by my hypotheses about each of f1 and f2. Here's the thing. I can apply my hypotheses, so I can replace f1, well, that's no larger than c1 times g1, and f2 in absolute value is no larger than c2 times g2. And the reason that's true is that I've assumed that n is greater than or equal to n star, and n star is greater than both n1 and n2. So I've intentionally put myself in a world where n is large enough that I can apply both of these inequalities describing my big O relationships. Okay, so now I continue. So what do I know about C1 and C2? Well, hey, guess what? C1 and C2, they are both less than or equal to C star. So I can replace C1 and C2 with C star, and that will only increase this expression, so I can keep my chain of inequalities going. So C star is greater than or equal to C1 and C2. And guess what? I'm still going on my chain of inequalities, so my next maneuver is to say, hey, similarly, if I replace G1 with just G and G2 with just G, well, what's G? It's whichever of them is larger. And so if I replace something with something that is larger than or equal to, I am going to continue to not decrease the result. So I'm going to have that my expression is continuing to only grow, so I'm developing an upper bound. And here we are. That's just two copies of C star times G of n. I assumed this for any choice of n greater than or equal to n star. And so my witnesses are 2 times C star, that's my witness for C, and N star. Those are my witnesses for any choice of N greater than N star. This absolute value is bounded by 2C star times G of N. So I've proven that this sum, f1 of N plus f2 of N, is in big O of G of N. In other words, whichever the bigger big O relationship is, that one is the one that's going to dominate the sum. This is the mathematical content, the formal proof behind the idea that only the leading term matters. So here, for example, if I look at n squared plus 2n plus 1, guess what? This is big O of n squared, this is big O of n, this is big O of 1. I can just preserve the n squared and find that this whole thing is big O of n squared. So this is the mathematical formal argument that justifies only focusing on the leading terms.